And there we are. Okay, this is the part 2 for our Chemistry 2330 review. I'm going to go over chapters 12 through 16 real quick, and then we'll have time for questions and answers. Of course, I hope you all have questions that you've brought to us. If you already have your question ready, you can go ahead and start typing in the chat room. But let me go ahead and try to hit some of those things in chapter 12 through 16 to let us see where we're going with the system. So chapter 12 was the beginning of our use of the carbonyls. And so the carbonyl is a functionality used in aldehydes, ketones, carboxylic acid derivatives, and we're also using it to enhance the acidity of alpha hydrogens. So it plays a role in all of those chapters, okay, which is chapter 12 through 15. So the first thing we want to do is identify an aldehyde. An aldehyde has that carbonyl with that H on it. A ketone is a carbonyl with 2 carbon bonds to it. Okay, and so this makes it very useful and synthetic. But the other thing it makes it is it gives us this polarity, okay? And we have dipole-dipole interactions, and that's the major driving force with its physical properties, okay? So that being said, it also, because of that partially polarized bond, we have that partially positive section and that partially negative.
So there's like the main.
Every ingredient has to start with C.
It gives us an opportunity to attack the carbonyl carbon with a nucleophile. And we learned about nucleophiles, of course, in our alkyl halides chapter when we were talking about SN1, SN2. All those same nucleophiles react with these to create this new tetrahedral intermediate. Now, if you have a good leaving group over here, you can regain that carbonyl. And we see that in the carboxylic acids. But the rest of the time, we're actually going to create a new tetrahedral center. And so we end up with alcohols and other reactants like that when we react things with that. We also learned about a new nucleophile, and that's the Grignard reaction right here. That's where we've created a partially negative charge on carbon, which has, when we think of it as polarized, it has a lone pair right here on the carbon, and it's our nucleophile that we can use in that attack. And we use this to attack aldehydes to make our, we can make secondary alcohols with that. If we attack formaldehyde with this, we can make a primary alcohol. And if we attack ketones with this, we can make a tertiary alcohol. Okay, so that's one of the cool things about this new type of nucleophile that we didn't introduce earlier, but this is introduced here in the carbonyl section here. And so, like I said before, if we attack formaldehyde, we already have 2 hydrogens on the carbonyl carbon, and they stay on the product and give us our primary alcohol. If we have an R group plus a hydrogen, and we attack it with another nucleophile, that's going to create 2 R groups, giving us our secondary alcohol. Then, of course, all ketones will end up giving us our tertiary alcohols. Okay, so that's one of the great reactions we have, and that's an addition reaction onto that. The other reaction we learned about in this ketone chapter is the fact that you can form this eno-keto tautomerism. And sometimes, even though there's very little of this in most of the cases, that is the reactive species, okay? Because it has a double bond, and we can add things like HBr or HCl across that double bond, okay? So the other thing in aldehydes and ketones is we figured out how we can make them by either oxidizing things down or reducing them. So the first thing we learned is that ketones don't oxidize. They are already as oxidized as they can, except in a very special case, which we didn't cover here. But aldehydes can be oxidized a little bit further, but they don't stop at just something like a ketone. They go all the way to the carboxylic acid. Okay, so anytime you use chromic materials with that, you can get all the way to the carboxylic acid. Remember, if you had a primary alcohol, you have to use that special PCC to make it stop at aldehydes. If you had a primary alcohol and you gave it the chromic acid, it would convert it to the carboxylic acid as well. Then the next thing we learned about the carbonyl is that we could reduce it down, okay? Aldehydes will create primary alcohols and ketones will create secondary alcohols. And we know we can use the same thing we used for regular double bonds, which is hydrogen with palladium catalyst. However, because of the reactivity of that carbonyl compound, we have two new selective reagents, sodium borohydride, right here, and lithium aluminum hydride that selectively add across that double bond and don't tack carbon-carbon double bonds, only the carbonyl. And it has everything to do with creating this hydride ion, which acts as our nucleophile and attacks the carbonyl carbon first. And then when you acidify the reaction at the end, you regain your protonated alcohol. So this is where we first introduce the sodium borohydride and lithium aluminum hydride. And remember, we use lithium aluminum hydride further on because it's required to reduce down esters. So we can use it selectively for sodium borohydride for aldehydes and ketones, but if we go to esters, we have to use the lithium aluminum hydride. Okay? Everybody still here? All right, yay. Okay, so in the naming of the carboxylic acids, we want to look at something like the diacids here are probably the hardest thing that don't quite fit all the other nomenclature rules. And that has to do with remembering that you have to count the carbonyl carbons as part of the parent chain. So that's why it's ethane dioic acid, because those carbonyl carbons are the ethane. So that's the one thing I wanted to pull out from the nomenclature here. Other than that, all those other nomenclature rules we talked about in review part 1 apply. Okay. Now, one of the things we learned about the carboxylic acids is that an inductive effect can change the strength of the acid. The more electron density you pull away from your anion here, the stronger that acid becomes. So here, going from 3 hydrogens to replacing it with 1 chlorine, which is a lot more electronegative, increases the acidity. And then by adding another one and another one, you can increase that acidity even more. But remember, that inductive effect is decreased as you move that electron withdrawing group away from. Every bond that moves away from that carboxylic acid, it decreases it significantly, like double and triple. So the best use of the inductive effect is to have those electron withdrawing groups, those electronegative atoms, next to the carbonyl with the carboxylic acid on it. Okay, any questions on acidity of the carboxylic acids and how to use them? Because the next thing we want to do is we want to look at reducing those down, okay? And like I said before, we can reduce down the carboxylic acid using lithium aluminum hydride, and it takes it down to a primary alcohol, okay? So it'll, not only does the lithium aluminum hydride take aldehydes down to primary alcohols, but it'll also take the carboxylic acid down, okay? Sodium borohydride will not work. You must use the lithium aluminum hydride in this, okay? Now, the other thing we learned about in the carbonyl chapter that was kind of interesting is the fact that if you have a ketone that is beta, okay, meaning that if we're 2 carbons over, this is our alpha carbon and this is our beta carbon. If we have a ketone on the beta carbon of our carboxylic acid, we can make this 6-membered ring. This 6-membered ring helps decarbonylate the material to give us a ketone. So we can actually create something in our next chapter, chapter 15, that will have a carboxylic acid on it. And then by heating it and forming the 6-membered intermediate, we can lose that and regenerate our ketone. All right, I have a question here. How do you know which side the bond shifts to in the eno-keto form? Okay, very good question. All right, let's go back up to the eno-keto tautomerism slide up here. Okay, so when we have an enol, and in this case here, it is symmetrical, right? So the fact is it's the same on either side, Okay, so in this particular form, it doesn't really matter which way it goes to. However, what we do know is that it actually follows Zaitsev's rule if you have a choice. So for example, I'm going to draw a different compound here. I'm going to draw this compound right here instead. Now, because of Zaitsev's rule that says you want to make the most substituted alkene, okay, that means the more likely contributor to the enol keto tautomerized thing is going to be the one with the double bond that is more substituted. Oops, have to erase that one. Oops. So it's going to give us this one is more stable than the other possibility because the double bond created is more substituted. Okay, does that answer your question about which side the bond shifts to in eno keto tautomerism? Oh, I haven't emailed out the first group project yet. I will email that out right at the end of this. Okay, answered that question there. Let me get through this review and then I will email it out. Okay, so we have this use of the enol keto tautomerism again to give us our 6-member transition state, which allows us for the leaving of that carbonyl. And again, we use that in chapter 15 when we create things with the Claisen rearrangement or the Claisen condensation because we are reacting esters. All right, so let's move on to derivatives of the carboxylic acids. And the first and most reactive derivative, and these are reactive, the more reactive are on the left. So these are most reactive. Most reactive, going to least, right here. So we have acid chlorides right here. We have a chlorine electronegative atom bonded to the carbonyl. The anhydride is the next most, the ester, and then the amide. And remember that the base strength of the leaving group is what drives that reactivity. The chloride is a chloride ion. That makes a very strong acid when it's protonated. The amine is the least acidic of this set. And so you can think about the amine being the strongest base, therefore it's the least reactive to the hydrolysis. But notice in each of these derivatives, we make that derivative by losing water, okay? And that means each of these derivatives will react with some water in some way. For the first two, they react spontaneously with water. Right here, we have to start adding an acid to it, right? With the an acid or a base to hydrolyze that. And here we have to add a very strong acid or a very strong base to hydrolyze that. Okay. Now, similar to what we saw in the ketones and the aldehydes, we can also get attack at that carbonyl carbon by nucleophiles. But because of the fact that we have some leaving group, either a chloride or an acetate or something as a leaving group, we can actually have it leave and regenerate our carbonyl. So instead of just getting an addition reaction at that carbonyl, we can get substitution reactions at that carbonyl, okay? And so that is one of the more unique things about this compared with aldehydes and ketones. Because when you have an aldehyde or ketone, you will have a hydrogen with a negative charge leaving, which is a very bad leaving group, or a carbon with a negative charge that's leaving. Those are the only two choices in aldehydes and ketones. In the case of the carboxylic acid derivatives, we have OH, we have alcohols, we have acetates, we have chlorides. So those make it much easier for it to reform the carbonyl and lose that weaker base in that system, okay? So since all of these derivatives are made with the loss of water, all of these derivatives actually can be hydrolyzed by water. okay? Now, I said before, these are spontaneous. They happen all by themselves. They don't need any catalyst at all to do them. However, once you get to the esters, you have to have a driving force. And you can use a base, which is called saponification, and it creates the carboxylic acid salt. Or you can use acid and water, and that, of course, creates your carboxylic acid and an alcohol. When you go up to an amide here, you have to use much more rigorous conditions. You can use acid or base for this as well. And in the case of the base, you again form a salt. I must have hit the side of my iPad. In the base, you form a salt that you have to add acid to at the end of the reaction. And in the acidic, you form a quaternary ammonium salt as your product as well. Okay, so because acid chlorides are the most reactive, you can use acid chlorides to make all of the derivatives. You can use them to make anhydrides, esters, and the amides, okay? So that is a very nice thing to do because it's the most reactive. However, once you have created those less reactive ones, they become harder and harder to make by more than one route. For example, if we go down to here, the summary of reactions with just alcohols, let me blow that up a little bit. All of these, the acid chloride, the ester, the acid chloride and the acid anhydride will react with alcohol spontaneously to generate an ester and some kind of leading group. In the case here, it's in the case here, it's HCl. In the case here, it's the carboxylate or the carboxylic acid. We can exchange them using our transesterification with another alcohol right here, but the amides don't react with alcohols, okay? So the amides will react with strong acids and bases in water, but will not react with alcohols. So we cannot generate our ester from an amide, okay? So now let's see what about reacting each of these substituents with an amine, or in this case, ammonia. Again, the acid chloride will react spontaneously, but requires two equivalents because we need to make a salt. The anhydride will react spontaneously, but it will also need two equivalents because we generate a salt. In the case of the ester, we only need one equivalent because we're creating neutral. Sorry, I'm not this popular. Why is this happening to me? There we go. Okay, I apologize for that. So when we react an ester with an ammonia, we'll create the amide and a neutral alcohol. However, if you already have an amide, you cannot react it. There is not enough of an amine or an ammonia strong enough to react that system. So again, it all goes to base strength. There's nothing that's going to drive that reaction. Okay, so that brings us to the summation chart here. And this is what all of those four charts there were telling us, is that if you have your acid chloride, and the way to generate it is using your thionyl chloride here, you can make all your other derivatives from it. But once you start getting to esters, you can only make amides and carboxylates from that, or other esters. Once you have your amide, the only thing you can do to it is hydrolyze it off, get to your carboxylic acid salt, and try again. So that's one of the really, this reactivity series is again driven by the basicity of the leaving group. And with that nitrogen anion being the most basic of the set, it will take the hardest to get off. Okay, shifting gears a little bit, another reaction, instead of doing a substitution reaction where we're actually substituting one group for another group, we're actually going to react across the double bond and create new products. So in the case of esters, if we have an ester, if we have two equivalents of a Grignard, the first one's going to come in, generate a ketone, or an aldehyde, and then that will react again with a second equivalent because there'll be a carbonyl to generate our final product. So in this case, we have a formate ester generates a secondary alcohol, but most esters, like this regular ester right here, will generate tertiary alcohols after the addition of two equivalents of your Grignard reagent. Because the first equivalent will come in and displace the alcohol group here and reform the carbonyl, and then the second group comes in and reacts with the second carbonyl and gives us our tertiary alcohol. Okay. Now, again, the only reagent we have for reducing down our esters is the case of the lithium aluminum hydride, and it'll always generate a primary alcohol because the first step is going to be, of course, removing the alcohol here and then reduction of the step. So that means we're going to end up with two hydrogens in this position, which gives us our primary alcohol and our whatever our ester group alcohol was made out of here. Okay, so that's the only reducing agent we have for that, but it doesn't work with just esters. If we have an amide, that amide will also be reduced, and only the carbonyl function will be reduced with this. Remember, the nitrogen's a really bad leaving group here, so all we're going to do is we're going to add hydrogen across this double bond here to give us our primary amide. If it was a primary amine, if it was a primary amide. But if our amine is substituted, this reduction does not eliminate, does not change anything on the nitrogen. It only takes away the carbonyl. So if we started with a tertiary amide, we'll end up with a tertiary amine. If we started with a secondary amide, we'll end up with a secondary amine. Okay. So that brings us to chapter 15. And I covered this yesterday as well about looking at the trend in acidity of alpha hydrogens. And the key with acidity in an alpha hydrogen is that hydrogen has to be next to that carbonyl. The carbonyl, being partially positive, is increasing the acidity of the hydrogen next to it, okay? So if we start with just the first introduction of it here, when we have these compounds here, there's no carbonyls on here. These are just the alkanes, alkenes, and alkynes, showing their very weak acidity, okay? The first time we have an alpha hydrogen that is activated by the carbonyl is in the case of an ester, okay? We have an electron donating group with the ester, and the hydrogen next to here can come off, okay? So it's just slightly more acidic than an alkynyl hydrogen because of that carbonyl, okay? Now, if we take away this electron donating oxygen and add a carbon to it, our acidity increases again, okay? So that's how our acidity is increasing with the increasing effect of that carbonyl carbon's partially positive charge. Now, in comparison, alcohol and water are just a little bit more acidic than that. Then the next compound we have with this marked carbonyl-based acidity, the alpha proton acidity, has a diester. We have two electron donating groups. Remember, those have lone pairs on them. Strawer-Lewis lone pairs here. And so that means they kind of, those partially positive charges are not as pronounced as if they were not donating group. But our acidity still increases because we have two carbonyls pulling on that carbon in the middle, okay? Now, if we lose one of those esters and turn it into a ketone, we go up again. Notice only one of the esters has been replaced with a carbon. Therefore, some of those electrons from that oxygen are gone away, and now this carbonyl is pulling harder than this carbonyl, and therefore our acidity increases. Okay. And then in our most acidic set, we have what we call our beta diketones. Both of these have carbons bonded to them. The carbonyl has its fullest partially positive charge, and therefore the alpha hydrogen in between those two is the most acidic of the alpha hydrogens. Okay, so that explains the whole trend we see in that. And we use this to our advantage when we're doing those aldol and condensations and our clays and condensations. Okay, any questions on that acidity trend real quick? So you have one carbon, you start with one carbonyl, an electronic donor group, then you go to one carbonyl, no electronic donor group, two carbonyls, and then you decrease the number of electron donating groups available to it. Okay, so it's not a mystery, it's definitely follows that trend. Okay, so the first thing we want to talk about as far as condensation reactions is, now that we know that those protons are acidic and we know how to pull them off with a strong base, what do? Well, they create an anion. That anion reacts with carbonyls because it becomes a nucleophile. And so if we have aldehydes and ketones, we call that the aldol condensation, okay? Now, most of the time, we just have one reagent in there and one base, and they react with one molecule of the aldehyde reacts with one molecule of the created nucleophile, which in this case is called our enolate. And it'll create in the case of an aldehyde, it'll give you a beta hydroxy aldehyde, or in this case, a beta hydroxy ketone in the case of the ketone. Okay, now remember what alpha and beta means. Alpha is this carbon here, and so our nucleophile is attacking a carbonyl. Our nucleophile was made, our negative charge was on this alpha carbon. So it's attacking the carbonyl of the aldehyde, yielding our alcohol on our new beta carbon. Remember, in this reaction, the bond we just created is this one right here. The sigma bond we created is the one right here. So that means the ketone is intact here and our new sigma bond there, generating our alcohol. So we always have our beta hydroxy carbonyl compound with an aldol reaction, okay? Now, the specialty part of that is when you want to be very specific about where you attack something, and the way you do this is you choose one compound that has no alpha hydrogens, which means you had to make the enolate out of the other compound. So of these two compounds, only the acetone can react to form the enolate ion, meaning that that has to be your reactive intermediate, has to be this one in the middle. The only carbonyl for it to attack is your other substrate, and that leads you to, you still have a beta hydroxy ketone in this case, but you knew exactly how it was going to be attacked because you had to make the enolate out of this one, and then it has to attack that one. That's why it's a crossed aldol condensation. So regular aldol condensation, you typically have one aldehyde or ketone and a base to generate your hydroxy compound. And in the crossed aldol, you have two and one base, and you'll make one product there as well. Now, don't forget, if you have two carbonyls on the same compound, you can make rings, but you're only going to make 5 or 6 membered rings. Do not make a 7-membered ring. Do not make a 4-membered ring, okay? You'll only make 5 and 6 membered rings out of these systems, okay? So that brings us to the claisen, and the claisen always has esters, okay? So in the case of the simple one right here, the aldol condensation, we can't make the enolate on this side because that's the ester portion. So we have to make the anion here. If we make the anion here, we have to then attack a carbonyl on another one somewhere else to give us our, this was our enolate here. I'm sorry, that is not. This was our enolate here. And when it came in, it displaced, it added to it, gave us that tetrahedral middle, but the alkoxide, the alcohol salt, could leave and regenerate your carbonyl. So your claisen condensation gives you a beta diketone. because the ester group, the alcohol of the ester group can leave, regenerating your carbonyl. Okay, so you'll always see an ester at the end of the chain, and then 2 carbons over, a carbonyl. That's the claisen with 2 esters. And just like with the crossed aldol, you can do a crossed claisen. And the way the crossed claisen work is the same thing. One of them has alpha hydrogens and one of them doesn't. Now this is really great because now you can say, well, in this case here, I only have alpha hydrogens here, which means this is where I'm going to form my enolate, which means this has to react with this, meaning I'm going to lose that as my group. And so this is going to be the beta ketone portion of our system, and our ester is the starting ester of the one we made the enolate out of. Okay, again, a crossed is 2 different esters, one of which has no alpha hydrogens. Okay, and just like the other intramolecular interaction, it has a special name called Dieckmann. And again, think 5 and 6 membered rings only. And again, you'll make your beta keto ester here. Okay. Now, once you have your beta keto ester, if you clip off your alcohol group and turn it into a carboxylic acid, that lets us do that decarbonylation we talked about in the previous chapter. Okay, because we can rearrange this to give us our intermediate with our, if we moved our hydrogen over here, we'll have the 6-membered intermediate. We can have that go there. Let's see, this goes here, and these electrons go there, giving us our final decarbonylated product after rearrangement. Remember that intermediate is an enol, but it'll rearrange immediately to the ketone. So once we have this beta carbonyl ester from our claisen, we can then clip off the ester and decarbonylate it to give us our new ketone. All right, questions on the aldol, the claisen, the cross claisen, the crossed aldol. And the intramolecular ones, always think 5 and 6 membered rings. That'll get you like almost 90% of the there on all of the aldols and the claisens. And again, aldols are always aldehydes and ketones. Claisens are always esters. Aldols always give a beta hydroxy compound. Claisens always give a beta carbonyl compound ester. Okay, so the next thing we can do with an enolate is we can use it to attack a conjugated carbonyl with a double bond. So they have to be right next to each other. And when we do that, we don't attack the carbonyl anymore. We end up adding to the end of the double bond. Okay, so instead of attacking at our carbonyl right here, we're going to end up adding to this point right here. So this works the best with some kind of dicarbonyl compound. So your diketones, your ketoesters, or your diesters. And it'll also work with amines because you can deprotonate these as well. And then once you create that enolate, it's going to, again, tack the end of the chain, and you will still have your ketone from your unsaturated substrate, and you'll have whatever carbonyl compounds you had on your starting material. In this case, we have a ketone and an ester. Okay, so this is called the Michael addition, and we typically call it the addition because it's not like the other ones where we're condensating, we're adding 2 things together. We're actually adding to that double bond. Now notice once you have this, you have a beta keto ester. Whenever you have a beta keto ester, you can hydrolyze it down to give you a carboxylic acid and then decarbonylate. Okay, so this is just showing you that you can continue on with those same reactions we have, you know, but this right here, just this portion here is the Michael. This is where we're creating our anion here. That's creating our new sigma bond there. and we maintain our carbonyls on all of the starting materials. Okay. All right, the last thing I want to do is talk polymers. Okay. So simply, you know, a polymer is any really, really big molecular weight, long chain thing of the same repeat units. Thermoplastics are very important because we can mold them and remold them and remold them and do what they have. Okay. I had a couple questions about step growth, and I really thought about it, and I said, you know, named for a functional group other than carbon-carbon bonds. Okay. So think about it. Polyamide is named for the amide functionality. A polyester is named for the ester functionality. So if there's an atom other than carbon in that main chain, the long portion of the polymer here, it's probably a stepped growth polymer. I still have not found one like that. So if we have an amide functionality in our chain, we have a polyamide. And we saw three ways to make that. One is to have one with a dicarboxylic acid. So we had a dicarboxylic acid on this side here. And we had a diamine on this side here, and you react one side with the other side, and it just keeps growing and growing and growing. The other way to do it is to do partially hydrolyze this bond here, and then it ring opens to give us a long straight chain. Remember, this is a 7-membered ring. We say 5- and 6-membered rings are more stable. So it's actually taking account for making that 7-membered ring the less stable part to ring open and make it longer. Then the aromatic version of this is what we call the aramids, and they form this fully aromatic polyamide that is called Kevlar. Okay, moving from the esters, most commonly we do this with a trans-esterification reaction. We take one difunctional alcohol and replace a single functional alcohol on two sides of a carboxylic acid ester. And that creates these long materials. Remember, elongation or stretching of these things make them strong and fibrous and crystalline. Not doing that makes them amorphous and transparent. Okay, a polycarbonate is kind of like a special diester. That's this functionality here, and so it's named for that. And then another special ester is the urethane. This is technically called the carbamide functionality, but we call them urethanes. So it's a carbonyl with a nitrogen on one side and an oxygen on the other, right here. So this is the carbamate group or the urethane, right here. So again, every single one of those polymers above had an atom other than carbon in that main chain, making them all condensation or step growth polymers. And in the case of an epoxy, we have our nitrogen acting as our nucleophile, ring opening our epoxy, and we end up getting the system like that. Okay. All right, just like in the step growth polymers where there's always an atom other than carbon in the main chain, chain growth polymers typically only have carbons in the main chain. And they're named for the material you made it from. So in the case of, if we started with ethylene as our material, we end up with polyethylene. If we started with tetrafluoroethylene, we're going to end up with polytetrafluoroethylene, or Teflon. If we started with dichloroethylene, we're going to end up with polydichloroethylene. Okay, but the cool thing about this is we like this reaction because all the mass of the monomers ends up in the polymer because we're creating a new carbon-carbon sigma bond. Okay, so to do this, we have 3 steps in our mechanism. We have to initiate the chain, and we do that by taking something that will break apart evenly to give us two single electrons or radicals. We typically use the oxygen-oxygen bond for that, so we call them peroxides. That generates that radical, And when one electron from the initiator attacks one electron of the double bond, it creates our new sigma bond, but also creates that new sigma bond, but also generates another radical. That radical will keep adding to any other double bond it can find until all those double bonds are consumed. So this is initiating the polymer, and then this is just going to keep growing and growing and growing. It's propagation. It's going to keep growing until you run out of things for it to react with, okay? Now, when you run out of things for it to react with, so you have, you know, a huge long chain here and a huge long chain here, and there's nothing else for it to react with, well, they have to react with each other to form a new sigma bond, but that terminates our radical, so we call that chain termination, okay? So it's a really neat and unique mechanism for how we've done things. We've done no other reaction like this. And that's why it's kind of an interesting way to sum up with that reaction mechanism. Okay, any questions about chapters 12 through 16? Well, I have it up here. Okay, unrelated. Okay, I have a question in the chat about spreading them evenly over the chapters. More or less, I mean, obviously there's fewer questions about, you know, molecular shape and stuff like that, but overall it's going to be spread out across the entire 16 chapters. There are some things that are, you know, they all have the same mechanism, so I might only ask that once, but some things will have subtleties, or, you know, an addition reaction using one material versus another material will give us two different questions. Like adding water across a double bond is one reaction, but adding HCl across a double bond is another reaction. But overall, yes, it'll be spread out across that. Okay. All right, while you're typing in there, let me go ahead and send the activity to everybody. Sorry, I forgot to do that this morning. I was, let's see, email, group activity 1. I meant to send it out yesterday, and I apologize. Documents. Open. Yeah, I finished it yesterday morning. Why didn't I send it out? All right. So everybody should be receiving that soon. And I've received it, so that's great. Okay. Could you go over the chapter 16 nomenclature question from the homework? I can. Let me get to our homework here. Chapter 16. Oh, yeah. We didn't cover that one in the book, did we? It would be polyethylene glycol. Or polyethylene oxide. But the, let's see, in theory, they're the same. So, but the correct answer is A, polyethylene glycol. And that will not be on the final because we did not have that in our chapter. But everything else we did cover. So, but yeah, I apologize. That was not in our chapter. Okay, I'm going to stop sharing. All right, now we're going to open up for questions for all chapters.
I have a question. So about the using.
We're right at 12:47. Do you want to go ahead and take about a 5-minute break and then come back with some questions?
Sure.
The thunderous applause suggests that. So, okay, I'm going to go ahead and end this and stop recording. Stop